we've been talking about valence electrons, and we want a way to represent these valence electrons so that we can communicate how reactive or not a particular element is. One way to do that is to use a Lewis dot diagram. A Lewis dot diagram is a representation of an atom. There are also ways to represent molecules, but right now we're focused on atoms that show all of the valence electrons of that atom. So another name for this is electron dot notation. But the procedure is to determine the number of valence electrons. Remember, these are only the s and p electrons, so there's 8 electrons max. You write the element symbol, 1 or 2 letters, always starting with a capital, and you place the appropriate number of dots around the element symbol. So the way I like to do this is I like to imagine a square around the element symbol. And here I've got element X. X isn't really an element on the periodic table. I'm just inventing an element here. I'm imagining this red square. I'm not drawing the red square. I'm just imagining it. And then let's say that X has 8 electrons. So I'm going to draw my electrons in pairs, just like in orbitals, but I want to place 1 electron per side before I start pairing my electrons. So this is, again, just like the orbitals, like Hund's rule, the empty bus seat rule. You don't want to pair up the electrons until you have to. Keep the electrons as far apart from each other as you can for as long as possible. So how does that work? Well, if I put electron number 1 over here on the right, then electron number 2 should be as far away as possible. And then I should keep electron number 3 as far away as I can, and same thing with electron number 4. Then for electron number 5, I can start doubling up. Electron number 6 has to be doubled up, again keeping it as far away as I can. Electron number 7 doubles up, electron number 8 doubles up. So I don't actually care that electron number 1 goes here. Electron number 1 can go up here. The point is that then electron number 2 has to be as far away from it as you can get. Again, that square, we just imagined the square to help us place these orbitals, place the electrons, but it's not actually part of the Lewis dot diagram. One exception to this electron placement rule is helium. Because helium is in the first period, it only has 1 orbital. Therefore, we don't spread out its electrons on opposite sides. We don't do this. Instead, we draw both electrons on the same side because we only have that 1s orbital, so those 2 electrons are, in fact, close to each other. So let's practice this. Beryllium has this electron configuration, 1s2, 2s2. Therefore, it has 2 valence electrons, and its Lewis dot structure looks like this. Carbon, its electron configuration is 1s2, 2s2, 2p2. Therefore, it has 2 plus 2 is 4 valence electrons. Only count the second energy level. And therefore, we draw the 4 electrons as far apart from each other as we can around the carbon symbol. Oxygen, its electron configuration is 1s2, 2s2, 2p4. So it has 6 valence electrons. And we draw 1, 2, 3, 4, 5, 6 electrons around the oxygen. Notice that 2 of them are doubled up and 2 of them are singletons. And then selenium, its electron configuration. Be careful when you count those valence electrons. It only has 6 valence electrons. We add only those electrons that are in the highest energy level. We don't count electrons in the 3rd energy level. And selenium has a similar electron configuration to oxygen, which is not surprising because selenium is in the same group as oxygen, group 16. Here's a kind of summary table of Lewis dot diagrams for all of these main group elements. Notice the repeating pattern. Everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Everything in group 13 has 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and mostly we have 8 valence electrons in group 18. The exception to that rule is helium. I hope this helps.